Welcome to the Distant Curve Severe Weather Analysis for Broome. I'm your host, and today we are diving into Friday, December 19th, 2025. If you find this analysis helpful, please like and subscribe to support continued severe weather analysis. Broome is looking at a genuinely concerning setup this morning. The atmospheric profile shows enormous energy waiting to be tapped. Let's break down what's happening in the skies above Western Australia. We're looking at the morning sounding from 10 a.m. local time. And this is where the story begins. The Skew-T diagram shows a mixed layer CAPE of 3,380 joules per kilogram. That's exceptional for Australia. Think of CAPE as energy coiled like a spring, waiting to be released. The surface temperature sits at 31.5 degrees Celsius with a dew point of 25.7 degrees. That means the air is loaded with moisture. The green parcel path shows where rising air mass would travel, and notice how far it goes, all the way to the upper atmosphere. There's virtually no cap holding things down. The LCL, or cloud base, is only 753 meters above ground. This means if storms develop, clouds will pop up quickly and dramatically. The lapse rate, how fast temperature drops with height, is exceptionally steep at 6.4 degrees per kilometer. All of these elements signal that the atmosphere is primed, loaded, and ready to explode into severe thunderstorms. Now let's look at what happens this afternoon. The enhanced Skew-T diagram shows something remarkable. Multiple parcel types all painting the same picture. We are showing three different parcels: the surface-based parcel at the bottom, the mixed layer parcel from 100 hectopascals up, and the most unstable parcel found through the lowest 300 hectopascals. All three show massive red and pink shaded areas. That's CAPE, the fuel for storms. The mixed layer parcel dominates our analysis and shows over 3,000 joules per kilogram of energy. The surface-based parcel actually shows even more, over 5,000 joules per kilogram. The massive pink shaded regions tell us there's enormous potential for strong updrafts. The green parcel paths show where air would rise if forced to do so. Notice how high they go, well into the upper atmosphere. The environment profile, that red line on the right, shows how dramatically unstable the atmosphere becomes once you force air to rise. There's virtually no blue shaded CIN, or CAP, in the low levels. The transformation from morning to afternoon will be dramatic. As the sun heats the surface to around 31 degrees, that additional warmth will make the parcels rise even more explosively. This is the classic setup for supercells and severe hail. Now let's look at the wind profile and what it means for emergency services. The hodograph, that's the curved wind vector diagram, shows how wind direction and speed change with height. Starting at the bottom in dark blue, we see the near-surface winds. Moving upward through the color spectrum, the wind vectors rotate significantly. The green section shows mid-level winds around 3 to 6 kilometers altitude, where the shear is most intense. By the time we reach upper levels in yellow, wind speeds peak above 20 meters per second. Look at the bunker's right mover vector, that red star labeled RM. It points toward the northeast, which means if right-moving supercells develop, they'll track toward the northeast at roughly 13 kilometers per hour. The 0 to 6 kilometer bulk shear is 15.2 meters per second. That's substantial and well above the 15 meter per second Australian threshold for severe potential. The 0 to 1 kilometer shear is much lower at only 3.4 meters per second, which limits the rotation threat. However, the combination of high mid-level shear and moderate low-level shear could support rotating supercells capable of producing damaging wind. The hodograph curvature shows directional shear, wind direction changing significantly with height, which can generate horizontal rotation that's stretched into vertical supercell rotation. If storms organize, electricity restoration crews should prepare for destructive straight-line winds from the northeast, particularly in areas along the projected storm track. The SCP score of 6.08 and STP of 1.8 indicate organized severe potential. The Brunt-Väisälä frequency profile, that blue line showing atmospheric stability at different heights, reveals something critical for downdraft potential. In the lowest 2 kilometers, the N profile shows moderate values, indicating parcels are gently stabilized but not rigidly so. This is the boundary layer. Moving up through 2 to 4 kilometers, notice the N values drop significantly. This is key. Low Brunt-Väisälä values mean weak stability, which allows powerful downdrafts to develop. When rain-cooled air from a storm cloud falls through this unstable layer, it accelerates downward, gaining speed rather than being damped out. That's the environment for microbursts. The decape value from the sounding is 1,652 joules per kilogram. That's high. Combined with a downdraft velocity of 57.5 meters per second, this signals extreme microburst potential. The yellow highlighted area shows a superrefraction layer, and the orange bands show elevated duct layers. These are technicalities, but the main point is clear. The mid-level stability profile strongly supports intense, organized downdrafts. If a supercell develops over Broome, microburst damage is a genuine threat. Wind gusts could exceed 100 kilometers per hour in localized areas. The hail growth layer extends from the 700-meter freezing level up through the -40-degree region. Plenty of depth for large hail to develop. With ship index at 10.4, large hail is certainly possible if storms develop. Emergency services should prepare crews to respond to both widespread wind damage and localized microburst impacts. Let's examine how the atmospheric conditions evolve through the day using the machine learning model comparison. The Cape evolution chart on the upper left shows the dramatic story. Energy builds through the morning hours, peaks around midday or early afternoon, then begins to decline as the sun gets lower in the sky. The Mel Cape climbs from around 1500 joules per kilogram early in the day, peaks near 3000, then falls back to under 500 by evening. This is the classic diurnal cycle. Heating in the afternoon generates the maximum instability. The lapse rate evolution in the lower left shows the rate of temperature decrease with height. Notice the lapse rate steepens dramatically in the afternoon, reaching 6 to 7 degrees per kilometer, then becomes more stable again in the evening as the sun sets. This reinforces the message that afternoon hours from 1 to 4 p.m. local time are the critical window. The deep layer shear chart shows that wind shear remains relatively constant throughout the day around 6 to 7 meters per second. And the cloud base evolution on the lower right tells us that LCL values dip lowest in the afternoon when heating is maximum, then rise again as evening approaches. All of this points to the same conclusion. If storms are going to form and organize, it will be this afternoon during the peak heating hours. Friday, December 19th brings a significant severe weather setup to Broome. The atmospheric energy is remarkable, wind shear is substantial, and the moisture is abundant. If storms develop this afternoon, they could organize into supercells capable of producing damaging winds, large hail, and isolated microbursts. The critical window is from 1 to 4 p.m. local time when heating is maximum. Always consult the Bureau of Meteorology for the latest official warnings and forecasts. This analysis is provided by Distant Curve Remote Area Telecommunications. If you found this helpful, please like and subscribe to support continued severe weather coverage for remote Australia.